us today. We're excited to walk through how spring thaw impacts rockfall risk and how that risk is changing across rail networks. We'll also be taking a closer look at rockfall monitoring, including where traditional approaches fit and how newer technologies are helping railroads improve safety and operational confidence in challenging terrain. In today's session, you'll see real-world examples, a breakdown of how these systems work, and practical insights into how monitoring and protection strategies come together in the field. Leading us through the discussion is Will Becker, Product Manager of Obstacle Detection Systems at L.B. Foster. Will has spent the last 5 years working directly with this technology, and prior to that spent 5 years at North American Class I Railroad, bringing both supplier and railroad experience to this space. With that, I'll hand it over to Will.
Thank you, Meredith, and thank you everyone for joining us today. We appreciate you taking the time out of your schedules to be here. So first off, today's session is focused on spring thaw and rockfall risk, specifically how these risks are evolving and what that means for rail operations. This is a topic that's increasingly important because what used to be fairly predictable and seasonal challenges is now becoming a lot more dynamic. We're seeing changes in weather patterns, variability in freeze-thaw cycles, and more extreme precipitation events. And this period can be particularly difficult to manage, and traditional approaches that may have used to work well are starting to show some limitations. So we'll cover that risk, and then we'll transition into rockfall monitoring technology. We'll walk through how the detection has historically been done, what those systems are designed to do, and then where newer approaches are starting to add value, particularly with earlier awareness and more condition-based monitoring. The goal here is not just to talk about the problem, but also give you a framework for thinking about the risk during spring thaw and how monitoring and protection strategies can work together to create a safer and more confident operation. So with that, let's get into it. So I want to level set on how we think about spring thaw risk because it's often misunderstood. Spring thaw isn't a single hazard, it's really a stacking of multiple processes that start interacting all at once. So first you have a freeze thaw cycle where it's already fractured and loosened the rock mass over the winter. And then at the same time you have snow melt, which is introducing water into your system, and groundwater levels begin to rise. And then often early in the season, like this time of year, you start to see early rain seasonal events later on top of that. When all these overlap, you're not just weakening the slope, you're loading it with lots of water, reducing its internal strength at the same time. And this is kind of your highest risk window. One important nuance that I want to mention here is that the thaw phase itself can actually be more dangerous than the freezing phase. So during the winter, ice temporarily acts like a bonding agent within the fractures, but as soon as that ice melts, you lose the cohesion that the ice was bringing, and you bring pore pressure into the rock face. And so you're essentially removing support and adding pressure, where the conditions are very conducive to rockfall, and this is when you start seeing the events. So from an operational standpoint, this creates a real challenge. Early in the season, slopes that look stable in a visual inspection may become weak. Everything appears intact, but subsurface conditions are changing rapidly. Water's moving, pressure's building, and fractures are opening. So, this is a period of time that we really need to have our condition-based approaches in place to run a confident operation. Now, historically, I think we've all known, we know where these risk areas are, but I think it's important to understand that these risk areas are changing because the problem isn't the same as we've always managed. So there's a couple of reasons for that. First, we can point to warmer winters, which are fundamentally altering the way that we have failure patterns. So in areas that were staying consistently frozen, we're now seeing more temperature swings between freezing and thawing and freezing and thawing. So this increases the number of freeze-thaw cycles that the rock face sees, which means more progressive damage to the rock mass. At the same time, there's been heavier precipitation events, which are becoming more common. So instead of a gradual thaw, we're seeing these big rain events with rapid saturation. And the key shift here is that slopes are crossing failure thresholds more frequently and less predictably. So what used to be a really defined spring thaw season is now more fragmented, and you have a lot of these event-driven failure areas. When you're looking in the Western rail network specifically, you've been hearing the term atmospheric river. They're becoming a bigger factor. These high-intensity moisture events deliver huge amounts of rain in a short period, oftentimes on top of snowpack, and the combination can rapidly accelerate snowmelt, drive infiltration into your rock face, and trigger both rockfall and debris flow in corridors that may have historically not seen that level of stress. And then one last point that I wanted to touch on is wildfire. There's been a lot of big wildfires out in the West specifically, but actually all throughout the United States, Canada. These wildfires are increasingly a part of the system. So one thing to think about here is that a burn slope will behave very differently the following season. You've lost the vegetation, you've lost the root reinforcement, and the soil itself can become hydrophobic. So at that point when storms arrive, specifically during the spring, you get very rapid runoff and debris mobilization. The USGS did modeling of this actually that quantifies the burn severity, basin geometry, and rainfall to estimate debris flow probability. But the main takeaway of their report is that last year's fire footprint often becomes this year's geohazard hotspot. And so that's something that needs to be considered as you move into spring, because these fires that happen in the summer, you're not going to see these failures generally until springtime of the next year. So overall, we're seeing a big shift from predictable seasonal risk to a more dynamic compound and location shifting hazard that has implications for how we're monitoring and managing our rail corridors. So building on the shift that we just talked about, the implication is this: the risk map itself is moving. Historically, railroads have relied on known problem areas with a track record of rockfall or slope instability. And while that approach is still important, they're no longer sufficient on their own. Because of all the changing weather patterns that we discussed, these areas where potentially had been assessed as low risk or lower priority are starting to behave differently. And so this is where we're really starting to say risk assessment needs to be done on a more routine basis. These risk maps that you have that highlight the areas that traditionally have shown problems may no longer be relevant. It's something that's definitely worth reassessing if you've had massive wildfires, large rain events, or if your area is now in one of those freeze-thaw areas. This is an area where you need to go back in, you need to look at your hazard map, and you need to update it because the risk areas are changing. Now, when we are talking about operational risk and monitoring for rockfall, I think there's one technology that everyone looks to, and that is the traditional rock slide fence. But even when installed, there's lots of reasons why you may not want to operate one. And first and foremost, I did just want to share a video of a rock slide fence, one of these heavy rain events that triggered a rock to come down, and where some of the drawbacks and limitations are when it comes to monitoring with a slide fence. So I want to spend a minute and just talk about what we saw there in the video. What that was is a major rockfall event that took place during a fairly heavy rain event, one of these atmospheric rivers that I was discussing, loosening debris and causing a rock to come down. This is in an area that was traditionally protected by a rock slide fence, and actually today is protected by our LiDAR-based rockfall monitoring system. One thing that I like to bring up when we're looking at that event in particular is that that detection was actually missed by the slide fence, but detected by our LiDAR monitoring system. And I want to talk a little bit about the slide fence background, and then we'll get into why these misdetections can happen. So what you're looking at here in this picture is a rock slide fence. It's the oldest detection system that's still in active use on railways today. And the technology itself dates back into the late 1800s, with the early implementation on a railroad called the Callander and Oban Railway in Scotland, where rockfall risk along the steep terrain, it needed a simple solution, and they came up with this rock slide fence. Fundamentally, today, the concept hasn't changed much in the last 140 years. It's a tensioned wire system where a rock hits the fence, the circuit breaks, and it signals an issue. Its longevity speaks to practicality. It's simple, mechanical, and it's been trusted for generations, but there are plenty of drawbacks to slide fences that would make me hesitate to putting one in today. Its core approach has seen very little evolution, and the main drawback, and this is what we saw in that video, is that it is dependent on something physically reaching the fence line and is very installation dependent. So when we're looking at a slide fence today, there's a couple of questions that need to all be yes for it to be effective. One is the installation covering the area in which a rock has potential to fall. And so, in this location, the answer was yes. They had a slide fence protecting that section of track where a rock could fall. The second portion is that installation consistent with the type of hazard that's presented? So there's a couple of different ways that a slide fence is installed. There are fences height. So is the risk towards the bottom of the rock face? Is it towards the top? There's also an additional canopy. This is something that is potentially hazardous when it comes to a slide fence, especially with changing risk areas. When we're looking at a potential rockfall event, let's say you installed a short slide fence 30 years ago, and it's been operating and maintained throughout that lifetime, that's based on an assessment of the risk at the time. If that risk potentially has shifted up the rock face, there's now more kinetic energy and potential for rocks to fall at a different angle. That slide fence needs to be installed differently to potentially catch that hazard. The third factor that comes into play when detecting a rockfall event is that slide fence needs to be maintained, and it needs to be maintained correctly. So the wires need to have proper tension on them. The circuit needs to be active, and those alerts need to prompt a railroad response. In the event that we saw, it was actually the third of these options that was the failure method. The slide fence wires weren't properly tensioned, and so there was too much of a gap between the wires at the bottom rungs, which allowed the rock to slip through and onto the tracks without being detected. The system does not have a method of self-checking that it is properly installed, that it is properly maintained, and that it will properly detect a rock. And so that's where we as a company came in and tried to think, okay, what are the drawbacks of a slide fence and how can we improve upon that? And the main one that we came upon is that a slide fence today is hoping that it detects a rock that may fall on the tracks, whereas our rockfall monitoring system is actively checking the tracks to ensure that the tracks themselves do not have an obstruction. So what does rockfall monitoring look like in an actual application? What you can see here is a basic methodology. What we do is we install a LiDAR unit that is shining laser beams over the tracks, and it does this 20 times a second over a 190-degree arc, and each one of these beams goes 100 feet. And so this is a very simple but deterministic way to determine if a rock is on the tracks. The question that we ask ourselves is, did that beam of light pass all the way past the tracks without hitting an obstruction? And if the answer is yes, we're going to say, okay, that section of track is clear. What you can see is when we place our LiDAR on the tracks, we see the tracks, but we also see in this image, there's a catchment basin and then there's a rock face. And so we're getting a lot of information. We can see the rock face, we can see the catchment basin, we can see the tracks. But I think it's important to remember one of the main drawbacks of a slide fence system is that it is prone to false detection from benign events. And so we understood that and wanted to minimize nuisance detections. And so the way that we did that is by implementing something that we call the detection zone. So what you can see here is what we call the detection zone. This is an area of track that we've determined and our rail partners have determined are critical for objects that are in this area to be detected and alerted upon. What this gives us the power to do is, unlike a slide fence, we are actively monitoring the track and saying continuously, is the track clear or is it obstructed? And, let's say a rock falls into the catchment basin. Well, we know about it. The alert is not the same as if a rock were to fall into the detection zone. It's a very reliable and expandable way to monitor a section of track. Right here, you're looking at about 100 feet, but this is something that can be scaled up to any size track. Now, one view is great, but we feel a lot more confident with our ability to detect rockfall when we have multiple views. And so what we do is on the left and right-hand side of the center LiDAR unit that we saw here, we'll install a separate LiDAR. This gives us redundancy inherently into the system, a very dense detector network where we're seeing any obstacle from multiple angles, multiple sensors, gives the redundancy that when we are seeing something, we're seeing it multiple ways, know exactly where it is, know the size of the object. And as a rail operator, this gives you the ability to operate confidently. When it comes to the system architecture, you can see that that example was 3 LiDAR, but we can scale this up to any size. And so in this example, you have 6 LiDAR. We will continue every approximately 100 feet adding an additional LiDAR unit, and this scales up indefinitely. The overarching redundant philosophy that we had discussed remains in place, and a continuous scan of your track envelope is achieved with this layout. Notably, these installations can take place essentially any place where you're considering a slide fence. This is a good place to put in a rockfall monitoring system. We've done a lot of work over the past several years to be in a place where we can install these anywhere. And so I just want to talk about that a little bit. So when we're installing a rockfall monitoring system today, there's a couple of key parameters that we're able to adjust to minimize disruptions. And this is based on our history of installing rockfall monitoring systems. So when we are looking at a site, there's a potential that they have some rocks that are fairly small that fall frequently that are not a hazard to trains. Well, because of that, we have the ability to adjust our minimum obstacle detection size. So we're only alerting you on trains and saying stop when an object of the minimum detection size or greater is seen. Additionally, we've seen many sites where there's all sorts of conditions. We've seen things from plenty of deer or bears or birds or even people on the tracks. And potentially we don't want to be stopping trains for those events. And so when we see an object in our detection zone, if it is not behaving like a rock, and if it is moving around the tracks in a way that is impossible for a rock, we're going to say, okay, that's a transient object. We're not going to alert on that. We're not going to stop trains for that. And then finally, there's plenty of clearance considerations. There are areas of track that are non-continuous, where the risk is, there's a risk in one section, a break, and then a risk in a separate section. We are able to customize our detection area to only protect the section of track that is relevant to your application. So this gives us a really strong foundation to keep trains moving anywhere. Some other enhancements that have been made to really bolster that is that a lot of these areas are in the middle of nowhere. And so recently this year, our system is now remote power capable. Additionally, plenty of places where we install foundations for LiDAR mounting is challenging. And so we have precast concrete foundations that can be dropped in to make installations cheap and easy. And then finally, and I think importantly, in an area where you may be considering putting in a slide fence, the operational cost of our system is comparable to that of a slide fence, but without the operational headache. And so, you know, today where we say that we are is when you are looking at monitoring, I just want Rockfall Monitoring to be on the list of a potential when it comes to installing a system rather than a slide fence, which comes with plenty of operational headaches, but also comes with plenty of safety headaches that we discussed. I think it's important to talk about how our system is built for rail operators. So first of all, we have a relay that reports clear or obstructed. Very simple to integrate into your signal interface. So when our system determines that an obstacle is on the track, or that relay will go from clear to obstructed, which can restrict your train signaling to allow for safe train operations. Additionally, we have a local HMI interface for system operation. So this tells you a lot of things as the maintainer, things like where the obstacle is, or seeing a picture of the event itself. Also, if the system needs maintenance, the local HMI, which would be in your signal house, tells exactly what the system needs to get it back up and running. So whether that's things like routine lens cleaning, or let's say a component were to get into a failed state, maybe it was hit by a rock, it would tell you that. So very easy to maintain. Additionally, so that's all on site, but we have the ability to take all this useful information and bring it off site. And so with a list of users, you can have pictures of the Rockfall event and a notification going to dispatch saying that there was an event. Here's a picture of what happened. And when that event clears, dispatch is notified. Additionally, since we have this connectivity, any maintenance that's required will be pushed up to the right list of maintenance personnel. And then lastly, I think, and most importantly, our system recently has been fully approved at a class 1 for slide fence replacement. And so today they are replacing slide fences with Rockfall Monitoring as the standalone protection. So in conclusion, I think the big takeaways are that in the springtime right now, the springtime thaw triggers these potential rockfall events. And, you know, today, I think many people would go to a traditional side fence as their solution, but they're expensive to maintain, they false alarm constantly, and they're a safety risk. Our modern LiDAR platform provides better protection without any of the operational drawbacks at a similar price point, and is the modern solution, whereas the slide fence is a 140-year-old solution. Investing in your monitoring today, what we've seen with our rail partners yields higher ROI in terms of train delay, operational efficiency, and maintenance force usage. But it also increases safety for your corridors. And so the main takeaway today is that L.B. Foster is here looking to partner with you. If you're looking into protecting corridors that have a rockfall risk, we are open to having those conversations, and we have a product today that is ready to meet those needs. Now I'll hand it over to Hannah, who's going to lead us through our Q&A portion.
Okay, we have some really good questions coming in here. As a reminder, at the bottom of your screen, if you have a question, go ahead and type it in, and we'll try to get to it. So we'll start with your first one here. Are these detectors also recording train passes, as AEI detectors do?
It absolutely does. So one of the criteria that we have in place for our Rockfall monitoring system is that we have a train presence input. With that train presence input, we're able to determine if a train is in front of our system. There's a couple of good reasons to do this. The biggest one is that when a train is parked in front of the system, obviously that's going to show as potential obstruction. So our system knows, no, there's a train in front. We do collate that information and we actually pump it into our KPI reporting where we say, this is how many trains passed our site and this is how many trains passed our sites unobstructed at full track speed. And so this is great if you're considering replacing a slide fence, because you put one of these in, we're going to start giving you a report saying, this is how many trains were able to operate at track speed without any slowdown.
Great. Is there a battery backup if the power goes out for any reason?
Absolutely. So our system runs off of a DC power supply. What we typically recommend is that our customers, when they install, they do provide a battery backup. We spec what that battery backup would look like, generally off of signaling batteries. And most of our customers opt with a 24-hour battery backup.
Great. Are messages from the sensors and detectors you describe being incorporated into the railroad's PTC systems? If not, should they be?
Yeah, so it depends. When we are tied into the signaling infrastructure, that would be tied into PTC. As of this time, we do not have any Rockfall monitoring systems installed on PTC territory, but there are some plans about getting a Rockfall monitoring system with a Class 1 that is using the technology onto their PTC track.
Great. How does the monitoring system provide protection on the slope?
Yeah, so I think this is kind of a fundamental change where, like slide fences, we are really detecting the rockfall event. We are not protecting from rockfall events. And so what we've seen is that we are in partnership with people who do geostabilization or mitigation, such as catchment barriers. And then we're on the monitoring side, where if that catchment barrier fails or if that mitigation event still leaves a risk and you want to monitor the tracks, that's kind of where we live. So we're monitoring the tracks for the operational risk. And then on top of that, there's a whole nother level of mitigation where, that's where we're talking about drapes or barriers or actual mitigation activities.
Great. How many feet of track does Rockfall monitoring cover?
So it can cover essentially any length of track. The main thing is that one control point can control up to a mile of track, but with multiple control points, you can continuously monitor as many feet of track as you'd like.
Awesome. How does the system handle two-track territory when a train is stopped on the closest track, thus obstructing detection of the adjacent track?
So there's two ways to manage that today. It depends on the operational concerns of the railroad. So, if a train were to stop in between the sensors and the adjacent track, obviously we cannot see the track. And so at that time, if you had LiDAR on one side of the track, you would need to report obstructed on the other side of the track. And so that would restrict the signaling on that second track if a train were to stop between the rock face and the LiDAR system. To get around that, one thing that can be done is that you can put LiDARs on both sides of the track to have no opportunity for that condition. So it's really a balance of operational concerns. So if you have double track and you just want to put in an operating rule that you don't stop a train in front of the rock face, that's one way to handle it. The other way is accepting the fact that you could go to a restricting signal if a train does that on the adjacent track. And then the third way would be installing LiDARs on both sides of the track so that situation can never occur.
Awesome. How are the individual wayside LiDAR units connected to the control unit? Does this require digging in cable?
It does. So the individual LiDAR sensors are PoE. We do have some customers that have been interested in potentially not digging in cable and having them above ground or even just scratch in. So that is a potential option, I guess, depending on your risk level. But today, every LiDAR goes to a trackside box through a PoE connection, and then from that trackside box back to the LiDAR on a fiber or back to the signal house on a fiber connection.
We do have a couple other questions in here, but I know we're getting close to our end time here. So if your question wasn't answered, will be in contact with you personally, and I'll let him close us out.
Great, thanks, Hannah. Thank you everyone so much for joining us today. I hope you've learned a lot about Rockfall Monitoring and its use case. If you're interested in Rockfall Monitoring or want to try it out, please reach out to our sales team. Our contact information is on the last slide there. We appreciate your time and hope to hear from you soon. Thank you.